Hey there, howdy folks, back here with another video where we are kind of moving on a little bit from what we have been studying. We have been looking at application of derivatives, and we're still going to kind of look at application of derivatives, but we're starting to transition over into the topic of antiderivatives. And if we think about finding the derivative as a mathematical operation that we can perform on a function, the antiderivative can be thought of as the inverse of that operation. All right? And that is where we are heading, folks. We are heading into that discussion of this inverse operation to differentiation known as the antiderivative calculation. All right. Well, to begin that discussion, we actually have to start with a discussion that goes back to the idea. Well, a discussion that's known as spend a little time exploring what we call the mean value theorem. All right. Let me bring this up here, folks. We do need to talk mean value theorem. Right? And antiderivatives. This is the topic we're heading into, right? And the mean value theorem has very important, what we would think of as implications, results that come about that are related to what we see in the case for the antiderivative of a function, right? There are some results of the mean value theorem that we have to take into consideration when we begin discussing the antiderivative function. All right. Now, what do we mean by the antiderivative function? All right. The antiderivative of f of x we think of as a function, right, whose behavior is such that when you take its derivative, it's equivalent to the function that it is the antiderivative of. Right? If we think about the antiderivative of little f being big F of x, big F's first derivative would be equal to little f of x. That would be the idea behind a derivative or an antiderivative function or an antiderivative operation. The antiderivative operation is actually going to allow me to find big F of x from little f. And what's going to be unique about big F is that its derivative would be equivalent to little f. That's where we're heading, folks, in our study. And to get there, we got to spend a little time with mean value theorem. All right? So we're going to talk mean value theorem. Now, to introduce mean value theorem, this is a bit of a nested idea. We have to also talk Rolle's theorem. All right? We first need to present Rolle's theorem. If we want or intend to prove mean value theorem, we're going to need Rolle's theorem in that proof, or Rolle's theorem. I don't know how you pronounce it. I always say Rolle, but Rolle's theorem here. Assume that y equals f of x is continuous over values of x in the interval from a to b, where the first derivative does exist for all x in that interval, meaning it is differentiable in that interval. If the output of the function f at a equals the output of the function f at b, then there must exist at least one value of x in c, well, x equal to c, in that interval from a to b, such that when you take the derivative of your function f, I should be careful there, at that value is c, it is equal to the value of 0. Right? It's known as Rolle's theorem. Right? It says, and we do have I do put this into other words and bring in an illustration to help, right? In other words, if y equals f of x is both continuous and differentiable over some interval of x, some closed interval we might think, where the endpoints of that interval are equivalent in their output, right, in their dependent values. The slope of the secant line passing through those 2 points at the ends, right? The slope of the secant line passing through those 2 endpoints at the ends would be equal to 0. And there would exist at least one point in that interval such that the slope of the line tangent to f would also be 0 in value. And we can note the following illustration here. All right. We can see in this illustration, we have our function in blue, right? And it exists over this closed interval from a to b, where f at a and f of b have both, right, the same dependent value. F of a equals f of b. Well, that means there is a secant line passing through these two endpoints that has a slope of 0. And there is these points that also exist in this interval from a to b, where the slope of the line tangent to the curve at those values would also be equal to 0, would be equal to the slope of that secant line. All right? This is what Rolle's theorem guarantees us. It guarantees us that if I have a continuous and differentiable line connecting these two endpoints that have the same dependent values, then there's going to be at least one location on that curve that connects those two endpoints where the slope of the line tangent to that curve is equal to 0, is equal to the slope of that secant line, which is also 0. Notice that is true at 2 points in this illustration. One above, between these two, we might think of endpoints on just this portion of the curve, or on these two endpoints of just this portion of the curve, it would be down here. Or overall, between these two endpoints, it would be at these two locations. But regardless, right, we would always have at least one value of c where the slope of the line tangent to the curve would be equal to 0. Now, we could prove this. Here's a bit of a proof. And to prove it, there are 3 cases we do have to kind of consider, right, in the above setup. And the above setup looks really, presents itself for 2 of the 3 cases. And you can kind of see the first case in there also. The first case is when your function itself is a constant function. It equals f at a, which is also equal to f at b. Right? That would be the case of having the constant function, the horizontal line that would stretch between just these two endpoints. That would be a horizontal line. That could be the first case we could consider. Or we could consider the case where f of x is greater than f of a. That for all x in some interval from a to b. That would be the case here in this illustration, where we might just be in this upper portion, where b is not down here, but we might put b at this first point. Right? Here. Here in this portion, f of x is greater than f of a, which would be equal to f of b if we put b at this endpoint. And notice that is also the value equivalency there, right? If we were to call this some other location, it would have an equivalent value to f at a. Or you have the case for what we see here, where f of x falls below those values. Right? In the proof, we have to consider these 3 cases. In the first case, well, as we had noted, the graph would have to exist as a horizontal line, implying that you would have a constant function. And what do we know about the derivative of a constant function is that it always equals 0. So at every value of x in that interval, the slope of the line tangent to the curve, right? The slope of the line tangent to what would just be the horizontal line, slope of the tangent line, is equivalent to the value of 0, right? And we have, again, an infinite number of locations of c in our interval from a to b, where f prime at c would be equal to 0 at every single value that would occur. In our second case, when f of x is greater than f of a, the extreme value theorem is going to end up implying that you have both an absolute maximum and an absolute minimum value of f on that interval. And if f of x is always greater than f at a, which equals f of b, then f of c will exist as the absolute maximum value. And at that f of c, f prime of c would be equal to the value of 0. Right? And there would be at least one location at that location of the absolute extreme maximum, right, where we would expect the slope of the line tangent to the curve to equal 0, as guaranteed by extreme value theorem. Right? Notice that is in this case here between these 2 points. On this closed interval between these 2 points, there's at least one value of c in that interval where the slope of the line is tangent to the curve at 0, because that's where we have our absolute maximum value in that interval. A similar result can be seen for case 3, looking at this location being an absolute minimum value between these 2 intervals. Well, between these 2 endpoints of this interval seen here. Right. Similarly, when f of x is less than f of a equal to f of b, again from extreme value theorem, there's going to exist at least one value of c in that interval where the slope of the line tangent to the curve would be equal to 0. It's going to be there at that absolute minimum value. Right? And that is proof. And I don't know if I can include that here. I probably should write this up. Let me do this. All right, folks, made a quick little fix there, and we're good to go. So I'll put a conclusion on that. And what we just showed here was that in each case of a function, all the different scenarios that you could have for a continuous function and differentiable function from A to B over some closed interval, whether it's a constant function, a function that's always greater than f at A and f of B, or a function that's always less than f at A and f of B, regardless of those scenarios, the extreme value theorem or just the fact that you have a horizontal line will always guarantee that there's at least one c in those intervals where the slope of the line tangent to the curve would be equal to 0. All right, that's an important fact to help us prove mean value theorem, which is far more interesting and useful to us. All right. Here's mean value theorem. It says assume y equal to f of x is continuous, right, over values of x in, again, some closed interval from a to b. Then what must be true is there must exist at least one value of x in that interval from a to b such that when you take the first derivative of our function f at that value of c, right, f of b minus f of a all divided by b minus a, right, this value here that we should be familiar with, it's known as, again, our average rate of change in our function over this interval from a to b, will be equal to the first derivative of our function at that value of c. And I probably should say here, add to this, where f prime of x exists in then the open interval from a to b. All right. Yes. Then there exists at least one value. I also need to note differentiability, right, in that interval as a condition. And that means then that if we're differentiable, there has to be at least one value where we're differentiable at, where the slope of the line tangent to the curve at that value, f prime at c, is equivalent to what we would say is the average rate of change in our function, where graphically that's going to correspond to the slope of the secant line passing through those two endpoints. Now in this case, again, it's a lot like Rolle's theorem. We're going to see it's similar to Rolle's theorem, except f at a and f of b don't have to equal each other. Right? If y equals f of x is continuous and differentiable, right, over those corresponding intervals, then there at least exists at least one location in the interval from a to b where the slope of the line tangent to f is equivalent to the slope of the secant line passing through these two endpoints. We can see here for this graph of this function f from f at a to f at b, you'll notice f of a and f of b are not equivalent, but there is this secant line dashed here that has a slope. And what's interesting here is the slope of the secant line, right, is identical to the slope of the secant line seen at these two other locations. these two other locations are guaranteed, or at least one of them is guaranteed by the mean value theorem. There's going to be, because our function is both continuous and differentiable between these two endpoints, there's going to be at least one value of x equal to c in between a and b, where the slope of the line tangent to the curve will equal the slope of that secant line, where we'll see this parallel behavior. And we see that here for this portion of the curve, and we see it down here for this portion of the curve, which again is kind of illustrating the case for above and below that secant line. Now, if we want to prove this scenario, here's the proof of our theorem. First of all, right, when we think about the average rate of change between those points, it is given by f of b minus f of a all over b minus a. Right? When f of x is continuous over x in the interval from a to b. And the equation of the line passing through these locations is actually then given by this equation here, where if we call this perhaps the slope of the secant line, we can see the slope of the secant line is this value being used right in here in our calculation. We are taking the slope of the secant line times this quantity x minus a plus f at a. We are using what again is that, and I think I've taught this in class, that point slope formulation for the slope of a secant line. And if that's the slope of the secant line, what we will then be able to do with that slope if we let h of x be a function representing the vertical distance between our function and this line, right? Where we note h of x then would be f of x minus this line. Now let me change this around. We did just kind of simplify that statement so it's not so bulky. Let me make those changes here. The value of h of x would be the difference between our function and the equation of the line that would be the secant line passing between our two endpoints. Where what we would notice about that function there, the difference function h of x, is that h of a would equal h of b, and both of those values would be equal to 0 in this above equation. If I plug in a or b, when a substitutes in, we'll end up with f of a minus f of a in this quantity, which will simplify to 0. And if I plug in b for x, the way the slope of the secant line works out is we'll end up with f of b minus f of b, both equaling the value of 0 in this calculation. Where from Rolle's theorem, the theorem we just went through, there must exist then at least one value of x equal to c in the interval from a to b, such that h prime of c, the derivative of our function h, at that value is c, which if we say h of x is equal to this, and we go through and note what that derivative is, it's going to be equivalent to this statement here, where again, this is the slope of our secant line, right? We'll end up implying that f prime of c will equal the slope of our secant line. Right? Which we know is, and I probably should have brought that in this way. Which is equal to that quantity f at b minus f at a, all divided by b minus a. And we had that above in our statement up here. All right. And I probably should put a conclusion on that. Let me do that real quick here. All right, folks. So yeah, I made that conclusion, put that right down there. Again, we were proving for y equals f of x, a function that is both continuous and differentiable on this interval from a to b. There has to be at least one value of x in that interval, all right, such that the slope of the line tangent to our curve at that value of x, we call it x equal to c, is equivalent to the slope of that secant line, that average rate of change in our function over that interval from a to b. And we just proved that above in kind of an unusual way. We did set up the slope of that secant line and note its relationship with f of x in terms of a difference, calling out that difference as h of x and using h of x to then develop through Rolle's theorem a relationship between the first derivative and the slope of the secant line. And with that relationship developed, we're able to, imply the result that we see in the mean value theorem. All right. Now, we're interested in the implications of that. We're going to get to those implications in one moment, but there is a problem type that we do sometimes see, right, that we are sometimes interested in, and that would be finding the location for x where the mean value theorem implies exists for a function, right? We might, for example, consider, right, we might say here applying the mean value theorem let's say it this way, to f of x equal to x squared plus 6x minus 5, right? That is both a continuous and differentiable function over all values of x, so it will be so over the interval from -8 to -2. Consider applying the mean value theorem. Well, one of the first things we'll notice, and to apply the theorem, is that our derivative of our function is equal to 2x plus 6. And the slope of the secant line over this interval from -8 to -2, if we roll through its calculation, is equivalent to -4 in value. Our vertical change is -24 units. Our horizontal change is 6 units. Which gives us a slope of -4 for the slope of the secant line. And the mean value theorem says that we're interested in the location where that f prime of x is equal to that value of -4, f prime of x being the value 2x plus 6. And we can see solving this for f prime of x, if we subtract 6 and divide by 2, this will be true when x equals -5. Using a little bit of algebra, we can find that result. Right? So x equal to -5 is the value of x. It is certainly in this interval from -8 to -2, where the slope of the line tangent to our curve is equal to the slope of the secant line. That slope being -4 in value. I do think I support this graphically. All right, there's our result that I just concluded. And this can be seen in the following illustration here. Here we have our function, that quadratic function. What was it? X squared plus 6x minus 5. I think that was it. All right. X squared plus 6x minus 5 from -8 to -2 along our x-axis. From here at -8 down to -2, we have this quadratic function. Well, the slope of the secant lines through the endpoints here is equal to -4. Horizontal distance of -20, or vertical distance of -24, a horizontal distance of 6. And there's one location on that parabola between those that interval from -8 to -2. That's right here at x equal to -5, right? Where the slope of the line tangent to that parabola, that portion of the parabola, is the same as the slope of the secant line. And you can see those two lines are parallel in our graph, indicating they have the exact same slopes. The slope to the dashed line is parallel to the slope of this tangent line. That dashed line being the secant line. Right? That is mean value theorem in action. Right? Using what it says to help us find this point of average change. Now, what's more important to us is probably the implications of mean value theorem. There are two important results that come about. The first, let me give a little bit of space here before we get into it. Right? Is that for y equal to f of x, if f prime exists and f prime of x is equal to 0 for all x, for all values of, and I should have x in there, I don't know why I don't, x in some open interval I, then f is a constant function on I. Right? Basically, if your derivative is equal to 0 everywhere on some interval, then you must be working with a constant function. That's one result of mean value theorem, and really that comes about from the Rolle side of mean value theorem. If you'll notice, Rolle's theorem is actually a simple case of mean value theorem. All right? It's the case where f of a equals f of b, and that slope of the secant line is equal to 0. Right? Well, Rolle's theorem says if that's the case, you're going to have a constant function. Now, we do prove that here, right? As we say, assume f prime of x equals 0 for all x in some interval from a to b. Then from the mean value theorem, what must be true is f of b minus f of a, that slope of the secant line, must be equal to f prime of c equal to 0. All right, let's maybe identify that here. The slope of the secant line must be equal to f prime at c, which must equal 0. Where with a little bit of solving, we can multiply both sides by b minus a. And when we multiply both sides by b minus a, we can end up saying f of b minus f of a must be equal to this value of 0. Or that f of b equals f of a. Right? For all values of x in that interval from a to b. Implying overall constant behavior in f, or f of x equaling n, equaling some constant value for some, well, some constant function, right, in its description. Yes. Right. That being proof. Now, this idea is what leads us to the following idea. Let me give ourselves a little bit of room here. Now, that first implication leads to this implication, or can be actually used in the proof of this implication. This implication says, well, letting c be any constant, if we assume the first derivative for function f and function g, these two different functions, are equal for all values of x in some interval from a to b. All right. Let's set c be any constant and assume that the first derivative for two functions f and g are equal for all values of x in some interval from a to b. then what must be true about f and g if they have first derivatives that are equal but are different functions is that they differ by nothing more than a constant. When we think about f of x can be thought of as simply being g of x plus some constant value. Or subtracting g of x from both sides, we can say the difference between f of x and g of x will always be equivalent to a constant. That does have some very important implication to it. All right. In other words, if two functions yield the same derivative values, then these two functions differ by only a constant value. And here's our proof. All right. What we do is we go ahead and assume that we have two functions f and g that are both have the same derivative. F prime of x is equal to g prime of x for all x in an interval from a to b. Implying that if we look at their first derivatives difference, if they're equal, they're going to be equal to 0 in their difference. Now, from our understanding of the fundamental rules of a derivative, if we call h prime of x the derivative, or the difference of those derivatives, then the difference of those derivatives, right, h can be written as the derivative with respect to x for f of x minus g of x. That can be used to represent the value h prime of x, where if those differences in our derivative equal 0, we can say h prime of x must equal 0. Right? H prime of x, then, if it equals 0 from the above idea, right, from the previous theorem, that implies that h of x must be equal to some constant function. Because any function that has a derivative equal to 0 over some interval of x, here it's this interval of x from a to b, if that equals 0, then that function must be a constant function. So h of x, the function representing the difference between f and g, must be a constant function or a constant difference. All right. So what that ends up implying then is, again, f of x minus g of x, because that's equal to h of x, must equal a constant value, or that f of x must be equal to g of x plus c. That what must be true about the relationship between f and g if they have the same derivatives is that they differ by nothing more than a constant. One is just a constant more than another, right, in their relationship. Now, we can show this in a quick little example here. We can consider two functions f and g. Here we might consider f of x equal to x squared and g of x equal to x squared plus a. Well, in this case, f prime and g prime both equal 2x. Right? They are two functions that both have the equivalent, will have equivalent derivatives. Where what we notice is if we take f of x and we subtract g of x, right, this is going to equal, if I set that up here, x squared minus the quantity, and I should be careful here, x squared plus 8, right? This does end up equaling negative 8 in value. I should point that out as being equivalent to negative 8. Right? If we think about f of x minus g of x, but they differ by nothing more than a constant. Right? That is true for any two functions that share a common derivative. Now, any two functions that share a common derivative are related to each other then, right? What we might note is f of x equal to x squared and g of x equal to x squared plus 8, because they share a common derivative, are also related to each other. And in fact, we can see the relationship through the library of functions. One is the other just shifted vertically 8 units. they're related in what we call a family of functions, right? A family back in that library, of the square family. And what's more specific here, though, a family of functions that can be summarized by what we call the antiderivative for those first derivatives, f prime of x and g prime of x. F and g, right, are both described by the antiderivative of their derivatives. All right? And that is going to be described by a family of functions. And that's the idea that we're going to lead ourselves over into with respect to the study of antiderivatives. A family of functions summarized by what is called the antiderivative for a function, right? We might say here an idea noted in the following development. I think I got my spelling wrong there. Development of antiderivatives. We're going to go through and develop that concept, folks. All right. That is the next part of the video here. And I'm going to stop this video here and come back to that video. Right. And talk a little bit about antiderivatives. This video is almost at 40 minutes, and that video itself is probably going to be about a 40-minute video. It has a few pages to it. Excuse me. Also. All right. What we did here, though, was we just brought up this last idea that if we're going to be talking about antiderivatives of a function, then antiderivatives of a function are more than just a single answer. What we're going to see encounter is actually an answer that exists as a family of functions. Right? When we think about the antiderivative of a function being another function, it's not only another function, it's a whole family description of functions, a whole functional description of a family of functions, right? In its description. And we see that develop here. And all of the Rolle's theorem, mean value theorem, and these two implications were really just some theoretical development to get us to this idea of the antiderivative of a function being a family of functions. A lot there, folks, for that one idea. But that is a very important idea to antiderivatives, we are going to see. All right. So I do have that video I want to put out for you here, folks. That'll be my next one, is to talk about antiderivatives. Right, to introduce you to the antiderivative and to go through some of the basic rules of antiderivatives. I think if we go through in total, there are 14 rules. 3 of them we might call our basic rules, and then the rest being rather specialized scenarios where we have to rely upon those rules for a lot of the process of integration. At least for a lot of the process of integration for a little while, until we look at developing some additional techniques later on in our study if we continue on into, well, what would be my study of Calculus 2. All right. But with that said, I think I'm going to end this video here, and I will see you in the next one to have that, that little study of antiderivatives. So, see you then.